Welcome to ClickMyProject.com. Let me discuss about the process, theoretical analysis of the coexistence of LTE-A signals and design of an ML-SIC receiver. Let me discuss about the abstract of the project. Efficient discovery and effective sharing of spectrum opportunities are the most challenging issues in a multi-channel cognitive radio network with multiple secondary users. Distributed opportunity spectrum access scheme based on sequential channel sensing in decentralized CRN. Different from the traditional spectrum sensing scheme, the scheme proposed allows a secondary users to sense many channels one by one sequentially in a slot. Opportunity spectrum access based on sequential channel sensing in decentralized CRN. Simulated annealing is a probabilistic technique for approximating the global optimum of a given function. Specifically, it is a meta-heuristic for approximate global optimization in a large search space. It is often used when the search space is discrete. The SC heuristic considers some neighboring states of the current states and probabilistically decides between moving the system to states and staying in states. These probabilities ultimately lead the system to move to states of lower energy. This approach jointly addresses when to perform sensing, which channel to sense, in what order, and how long to scan each channel. Let me discuss about the flow diagram for our process. Initially, design physical space within sensor sampling period. It is based on the sensor state in dynamic system, and also generated the cyberspace model, which are based on the sensor sampling period. And for the channel under consideration, its bandwidth W is equal to 2 MHz and a noise power on 1 milliwatt. The signal to noise ratio of the channel received by the sensor during the channel's busy period is -3 dB. Here adapted the Poisson channel model as described, with the average channel busy and ideal rates alpha is equal to 5 and beta is equal to 30 respectively. The sensing parameter epsilon d is equal to 1.2. The maximum sensing time is tau is equal to 250 units with the unit channel sensing time as 0.1 milliseconds. In a multi-channel scenario, the sensor date can be transmitted to the remote estimate via one of the orthogonal channels. The average busy and ideal rates for channel are determined. All the other parameters of these channels are set the same as those in the single channel scenario. To run the proposed OSSA algorithm before transmitting the packet, the sensor must check the channel state and transmit packet only when the channel is in its ideal state. Perform process with a single channel and multi-channel. A Lagrange multiplier is applied to the first constraint to transform for dual function. Propose a simulated annealing based optimal spectrum sensing algorithm to randomly search the sensing time. To deduct energy by each channel each iteration by only randomly generating a sensing time. Evaluate the objective Lagrange function each iteration of OSSA. Analyzes the computation complexity. The estimator runs the algorithm and finds the solution offline. It sends the solution to the sensor, which operates according to the solution from them. We'll be discuss about the running procedure for our process. Select the main.m file in the current folder, write the file and run for executing this process. Here we perform the ML-SIC receiver. Here basic OFDM blocks are implemented. And in this process we additionally include the ML-SIC receiver at the receiver side in order to improve the BR response, cumulative distribution function response, and also the theoretical analysis of our received signal. This process will take some time for execute. After executing, we analyze the performance. This is the transmitted signal for our 8 number of subcarrier, and this is the decoded signal when user M symbols are decoded. This is a error term in terms of user M symbols. This is the error result, and this is the error term when the signals are passed into the subcarrier, and this is the nth subcarrier of user M. There are 8 subcarrier here we have used. This is the variance of the error terms. This is the variance of the error term for every subcarrier, and this is the uniform distribution terms for our every subcarrier signal. This is the uniform distribution terms and combine the subcarrier for our single user, and this is the SINR response for a every subcarrier for a single user, and this is the SINR response for all subcarrier signals. This is the power spectral density graph by varying the sampling frequency in terms of megahertz, and this is the CDF, that is throughput cumulative distribution function for homogeneous deployment by varying the throughput response. This is the cumulative distribution function when by varying the uplink total throughput. For uplink communication, we analyze the cumulative distribution function result. This is the cumulative distribution for total uplink throughput for existing our and also our proposed work. And this is the bit error rate response by varying the number of users and compare with existing and our proposed result. This is the bit error rate response by varying the number of users and compare with existing and our proposed work. Finally, we improve the bit error rate graph, cumulative distribution and power spectral density by including ML-SIC receiver at the receiver part of our OFDM. Thank you.